Now we have Professor Christopher Budd, OBE. Professor Budd is a professor of applied mathematics at the University of Bath, and he holds many prestigious positions, including Chair of Mathematics at the Royal Institution of Great Britain and Director of the Center for Nonlinear Dynamics at Bath University. We're really excited to have him with us, and he'll be speaking about the connections between mathematics and art.
It's a great pleasure to be able to come to the SUMS meeting on what, of course, is Pi Day. And in the UK, where I am, is also Mother's Day. I'm sure it's a different day in the US, but it's a great great pairing of days today. And of course, whilst COVID in every way is a horrible thing, it has meant that we've developed these wonderful ways of working with each other and coming over to see each other through Zoom. And I'm really pleased that we can do that. So I'm going to talk today about the art of math. And the kind of one reason I want to give this talk is that my daughter is an artist. She's a fully paid up professional artist, mostly working in ceramic art. And she lives in a house full of other artists. And whenever I go off to see them and tell them I'm a mathematician, there's always a kind of stunned silence where they indicate to me that they think mathematicians are evil, soulless geeks. And my counter to that is to say, actually, the kind of difference between art and maths is really very, very small. And many great mathematicians, such as Donald Coxeter, who we're going to meet later on in this talk, basically think of themselves as doing art when they're doing math. And there is a whole conference called the Bridges Conference, which is a celebration of the links between math and art. And I've had the joy of having to speak at that a couple of times. It has a fantastic abstract book. I mean, the abstract book is a work of art in itself. And one of my main sort of points is that when you do creative math, then going from that to art is almost immediate. And also when you look at art, there's lots of really interesting math that you can kind of get challenged to do by doing that, by just kind of thinking about art things. So that's kind of what I want to talk about today. And because this is a meeting about math and illusion, I'm also going to try to show how when math meets art, you can actually start generating great illusions as well. But the story I'm going to tell will be sort of a historical story. I firmly believe that when people started thinking creatively, math and art were two of the things they started thinking about way back thousands of years ago. So it's a good way to think about math and art is to think historically how the two subjects have grown together. Now, I live and work in the town of Bath, which is quite an ancient town in the UK. It's about 2,000 years old, some of the buildings around where I live. But we're also very close to the country of Wales. And I love going to Wales a lot, mainly because that's the nearest mountains that I've got where I can climb in. But also there's lots of wonderful mathematical art that comes in Wales. And this is what is generally called Celtic art. And I'm sure many of you may have come across this. Of course, it's not just in Wales. You see it all over the world. And here is a picture of a Celtic cross. The cross itself, of course, is a mathematical symbol, and it's on a circle, which is another mathematical symbol. But I'm sure you can see inside the cross the beautiful forms of what are called Celtic knots. And Celtic knots are a lovely example where art meets maths square on. There is no difference between art and math when you come to look at Celtic knots. And I just love wandering around Wales, particularly going around churchyards and so on. But this art is also older than that. Just looking at the beautiful geometry on all the monuments or crosses that you find there. Here is a shot from a thing called the Book of Kells, which is a book which was created or written in around about the year 700 by monks. And you can find it if you go to Trinity College Dublin, which, by the way, has a great math department as well. And inside the university, there is a building where this wonderful book is held. and it's an illustrated version of the Gospels. And the monks must have just spent acres of time over it, because pretty well every page is an piece of art in itself, and almost every letter on that page is a piece of art. And here's the letter T. It's the first letter in the Gospel of John, and it's in the shape of an animal, which some people think is a snake, other people think is a lion. And you can see within the body of this animal the wonderful form of a Celtic knot. And immediately when you look at that, you can see geometry, and you can see also good mathematical questions that you might want to ask. So knots themselves are naturally a branch of math where you've got pure math on one hand, meeting applied math. I'm a mountaineer, as you've heard already. This is one of my books that I use. And whereas most of the math I do doesn't really make much difference to the world, if you get the knots tied wrong when you climb, then you come to a very sticky end. So it's good to get the math right on those things. And of course, there's been an enormous amount of mathematical investigation into the different types of knots, and still lots of open questions. And here are the first knots up to the 7-7. These are knots with no crossings, 3 crossings, 4 crossings, up to 7 crossings. And a knot is defined to be an object which you basically tie with one piece of string, which has no ends. And all of these wonderful designs here not only are mathematically very beautiful, but also have a great aesthetic quality. And you see these everywhere in Celtic art. Here's an example of the simplest type of knot, which is called a trefoil. And this is a bronze sculpture. And if you go to the University of Bangor, which is in North Wales, then as you enter the math department, this wonderful sculpture greets you on your arrival. We can ask ourselves then, how do you go about actually constructing the sort of knots that you might expect to see in the Celtic artwork? And this is where we can start going from the art to the maths, doing some more art and doing some more maths as well. So I was taught how to draw Celtic knots by no less than the Bishop of Gloucester at a workshop I went to on math and geometry. There's a tradition in the UK of members of the clergy often doing a chunk of math in their spare time. And to draw the simplest type of Celtic knot, you need to start with a grid, and the simplest grids are rectangular grids. And because we're mathematicians, it's good to classify such a grid. So I shall simply classify that to be a 5-4 grid on the grounds that it has 5 horizontal lines and 4 vertical lines. Okay, so there's our grid, and obviously we could have different types of grid. So example, here's a 5-6 grid. And the basic construction for the simplest Celtic knot is on the horizontal lines at the bisector of each square. You draw a cross with the leading diagonal going from top left to bottom right, and the one underneath it, a broken one. And then on the horizontal lines, sorry, on the vertical bisectors, you do the same construction, but now have the leading diagonal go from bottom left to top right. And that gives you a kind of a pattern of crosses. And then you basically start anywhere you like and follow your nose. It's not a particularly precise mathematical term, but I hope you get the idea, to produce a pattern looking rather like the one I've just drawn. Now, that is a Celtic knot, but patterns like this have natural applications. And the most natural application would be to see this as some sort of weaving pattern, where you might take a piece of string and weave it into that shape. It's often called a plaited mat. And some of the earliest examples of what I would call applied mathematics are sort of the weaving patterns that you see in clothing and also in fishing nets. And these sort of patterns here have been found in nets 7,000 years old, recovered from caves in the Mediterranean. So if that's a net with a piece of string, a natural mathematical question is how many pieces of string would you need to produce that net? And when you look at it, it looks fearsomely complicated, but actually when you get down and count them, you find you only need one piece of string to produce that net. So that's a net from a 5-6 grid. Here's a somewhat more subtle picture, one I kind of did earlier. So here is a grid where we have 4 horizontal lines and 8 vertical lines, producing what I would then call a 4-8 Celtic knot. And if you look at how many pieces of string are needed for that one, you find quite simply that the number of pieces of string you require is rather bigger. In this case, it is actually 4. Okay, what's the point of this? It leads us to a natural mathematical investigation. Oh, sorry, that's the picture I wanted earlier. Here's a picture with 2 on a 2x2 grid, where we get, in this case, 2 pieces of string are needed to draw that. It's done using exactly the same construction, and that gives us what is generally called a link rather than the knot. Okay, so here's a mathematical investigation. Nothing like as complicated as the one Percy told us about with the infinite random graph, but nonetheless a mathematical investigation anyway, which is one which was done quite early on in people looking at Celtic knots and making weaving patterns as a result. How many pieces of string are needed in order to make the knot on the grid pattern that we have. And we can see that if you have a 2x2, you need 2 pieces of string, 3x2, 1, 5x3, 1, 4x4, 4. Okay, back to my daughter and her artist friends. I like to try to explain to them what math is. Okay, it's actually rather hard. I was on the council for many years of the London Math Society, which is the kind of main learned body for pure mathematics in the UK. And we tried very hard at one point to define mathematics. And after a bruising series of discussions, we decided we couldn't do it, although we all kind of know what it is. And there's a sort of homework question for you. What is mathematics? But the reason I like doing this with my friends, or my daughter's friends, is to show what I think math is, which is basically the search for pattern. And with the Celtic knot example, and this is again very much what the ancients were doing when they were looking at this, we can sort of think about doing lots of experiments, looking for patterns, making hypotheses, checking our hypotheses against other examples, and then of course doing what we as professionals have to do, which is to prove the result using mathematical reasoning. Okay, this will of course come as no surprise to anyone in this conference, but does come as a surprise to many people when I tell them that math, as far as I'm concerned, is very much a creative experimental subject, with the added excitement of having to prove things at the end. Okay, I hope you've all managed to spot maybe what the pattern is here between the Celtic knot grid and the number of pieces of string, but in case you haven't spotted it, it's simply the greatest common divisor of the number of vertical lines and the number of horizontal lines. And it's pretty easy to check this on a finite number of examples. It's actually surprisingly challenging to prove the results. So I'm not going to prove it today. I'm going to leave this as a bit of homework for the sums meeting, is to go off and see if you can prove to yourself why the number of pieces of string on an MN grid is the greatest common divisor of M and N. And I'll give you a hint. It uses Euclid's algorithm, but done in a geometrical manner. Okay, so I went to one of these. Well, actually, I went to another conference I went to. I was invited to speak at the African Congress of Mathematics some 20 years ago as a representative of the UK. And I went along to this conference, and I thought, well, what should I talk about? I'll talk about Celtic knots. I mean, like, kind of fun, a bit different from something else. So I gave the talk talking about these kind of patterns that we'd observed, which went back in history. And a wonderful guy came up to me, a guy called Paulas Gerdes, who said to me, well, you know, you Europeans, you may think that this is old if it's a few thousand years old, but we've been doing this stuff in Africa for far longer than that. And he told me about the kind of way that geometry and art meet each other in Africa, about how many of these kind of results that I was telling you about have actually been known about in African art for much, much longer. And if you haven't got this book, get it. It's produced by the MAA, The Geometry from Africa. It's a beautiful book about African art and the math related to it. And in fact, there's quite a bit of illusion in there as well, because it shows how the art is used to tell stories and to surprise people through the stories that are told. So the basic type of art that Paulas Gerdes introduced me to was what's called sonar art. And sonar art works by using as your kind of canvas, as it were, the ground, which is assumed to be kind of a sandy type of ground. And you put dots in the ground using your fingers, and then you draw around the dots to produce beautiful geometrical designs. And whilst you're drawing around the dots, you tell stories. And again, this is where the mystery and illusion comes into the story. So on the left, you can see kind of how the construction works, drawing on the sand. On the right is the actual picture. And this is meant to be a picture of 4 rats who've kind of met each other into kind of some sort of unholy tangle of rat. What's the link with Celtic knots? Well, essentially, the simplest type of sonar pictures are mathematically essentially equivalent to the Celtic knots that I was just telling you about. In this case, instead of the number of horizontal and vertical lines, it's the number of horizontal and vertical dots. So on the left, we have a 3-4 dot pattern, and on the right, a 2-4 dot pattern. And then telling the stories, it was generally reckoned that the best stories were told if you drew the pattern with a continuous sweep of your finger. Those are called unicursal patterns. And on the left, you can see a pattern constructed using very similar rules to those used to draw the Celtic knots. And on the right, a pattern, well, with a different number of dots. And the number of times you have to pick your finger off and start again turns out again to be the greatest common divisor of M and M. And this was realized in Africa many thousands of years ago, and was possibly one of the earliest examples of people being aware of this property of numbers, the greatest common divisor. The proof is again done using a geometrical form of Euclid's algorithm, where you successfully reduce the size of the picture and down to the smallest one, which you can then do directly. Okay, so that's the simplest type of picture. There are many other types of sonar picture which you can go off and study and look at the symmetries and the number of times you have to take a picture, your finger off the soil. This is by far my favorite. I've drawn it on my board behind me, which is how I also do my lectures for my undergraduates interested, which is called the chase chicken. And this is the path that a chicken makes as it goes through a forest, as it wiggles to try to avoid a fox. So this is a story with a happy ending because it works. And if you want to learn more about the kind of construction of this, have a look at Paulas's book, and he'll take you through the symmetries and many things besides. So I really like these, nice and simple. It's math in your face. It's something I can show my daughter and her friends to show how the experimental and the rigorous sides of maths come together, and you get beautiful pictures at the same time. So let's move up from the Celtic art to round about the 10th century or thereabouts, where some of the primary mathematical art was being produced in the Islamic area, so North Africa and Southern Europe. And here we see absolutely beautiful patterns which have very, very strong geometry to them. Here's some more, and you can see that they're not just done on the plane, but can also be wrapped around the domes of the sacred buildings in the various cities in the Arab world. So Islamic art is absolutely beautiful and was very much influenced by the work of the Greeks and Euclid and ruler and compass constructions. And what basically these, what do I call them, mathematicians or artists, it's indistinguishable at this stage, did was take the basic ideas of Euclid using ruler and compass and use those to produce this beautiful and stunning artwork. So let's have a look at this. What is kind of going on here to make it so beautiful? Well, essentially, you've got a couple of things acting to do this. You've got the basic rules of geometry itself, and also you've got the very strong action of symmetry and periodicity in the development of the art that you're seeing. And all of these images that we see are examples of tessellations of either the plane or the rather more complicated image, well, the complicated surface that we see in the middle image. So Islamic art makes repeated use of designs which you construct essentially, as I say, using ruler and compass, and then repeat to fit together to form the basic images that we see. Okay, so where's the higher math here? This is going from Euclid's ruler and compass construction into producing pictures, but very quickly you end up doing much more sophisticated math. And the thing that you encounter quite immediately is the action of groups. Now, obviously, group theory in its kind of formalized form didn't arise till the 19th century, the work of Galois and people like that. But the basic ideas of group theory, the action of operations, the inversion of operations, the compounding of operations and so on, can be found in many of the early artistic constructions, so preceding the formal development by many, many hundreds of years. Again, this comes back to my point that a lot of art, being very creative, is anticipating some of the mathematical developments, or mathematics can learn from art as well as art learning from maths. So the basic factor that operates in many Islamic patterns is the Euclidean symmetry group E2, which essentially the transformations of the plane which perform preserved distance. So you might take a basic image such as a star or one of these other images here, and act on it by one of these group operations. So the simplest operation would be a translation, or you might have some sort of reflection, or you might have some sort of rotation, or the general member of the Euclidean group would be some combination of all of these. So that's how these pictures were produced. And then it was kind of realized fairly quickly that some of the pictures looked kind of similar and some of them looked kind of different. And you could start asking the question, what are the basic types of design that you might expect to see if you're doing these sort of operations? So here again, this is math learning from the art. And a wallpaper design is, and I'm sure you've all got houses with wallpaper. One of the nice things about Zoom actually is you end up working with people and you can see into their houses and see what their wallpaper looks like. It's great fun. Wallpaper designs are patterns which are themselves invariant under subgroups of the Euclidean group E2. And this led to a very interesting investigation, and the art led to an investigation of what sort of wallpaper designs there are. And here's the surprise. I mean, again, you know, I say math is a subject of mystery and amazement. you might think that there are an infinite number of wallpaper patterns, or at least a huge number of them. I mean, you know, you would have thought passively infinite's not unreasonable, given the amount of sort of things that you could do. But very, very counterintuitively, it turns out that there are 17. So there are 17 basic wallpaper patterns which have certain symmetries associated with them. And all other wallpaper patterns are, to a certain extent, well, they're all the same. They're just kind of detail differences in the way the actual pictures work, but the symmetries that are embodied in them are always one of these 17 basic wallpaper designs. That blows my mind. It completely blows my mind that you can sit down and classify all these patterns like this. And again, it's something that you can kind of talk about with artists as to say, well, look, if you are kind of constraining your work to keep the symmetries, and there seems to be some sort of link between symmetry and our aesthetic appreciation of things. I don't know why, but that seems to be how our brains work. Then that is going to kind of limit the number of things that you do. But it doesn't sort of stop your creativity, but it gives you some idea as to what might be are possible out there. And that really kind of blows my mind just to think about it that way. Okay, well, very closely linked with the sort of wallpaper patterns and the symmetries that I've just talked about are tilings of the plane. So tilings of the plane are how you can get objects to fit together to tessellate the plane. And here's a very nice example of a tiling of the plane by Escher. We're going to come back to Escher in a minute, which he produced in 1943. Escher, well, we'll learn about him more in a minute, but he was living in Holland at the time, which is an example of a periodic tessellation of the plane, done not using triangles or squares or anything boring like that, but done using these beautiful reptile shapes. And again, you can immediately see here art and math kind of slamming into each other to produce this beautiful picture here. Just as there are 17 wallpaper patterns, so there are 17 essentially different periodic tilings of the plane. And one of the simpler ones, which you often find on the floors of buildings or on walls. If you go to Spain, there's lots of these on the walls of the Spanish houses, is the Pythagorean tiling, which is clearly periodic tiling of the plane using squares and other squares, well, squares of different sizes. So for many years it was thought, well, that was it. There is no more. There are 17 tilings of the plane. It's all been done. What is there new? And this was a point where the mathematician became super creative. So Roger Penrose, who we'll meet in a minute in another context as well, asked himself the question, are there tilings of the plane which are which fit the plane, you know, objects into the plane, but which are not themselves periodic? And he came up with this, or variants thereof, which is an example of what's called an aperiodic tiling of the plane. So here we have two objects. One is a large diamond, which is in dark blue, and the other is a small diamond, which is in light blue. And these are kind of all joined together, as you can see. They are tiling the plane in a beautiful way, but there's no periodicity in this at all. This picture does not repeat periodically. It's aperiodic, but extremely beautiful nonetheless. And the Penrose tilings, rather remarkably, have now been found in crystals. So they're things called quasi-crystals, which adopt exactly this pattern. And they were discovered after Penrose had kind of come up with the idea of aperiodic tilings. There are various types of toilet tissue which have this pattern on them. which I believe was the subject of a law case about priority. And if you ever visit Oxford, and please do visit Oxford, it's a great place. It's where I did my PhD. And you go to the Andrew Wiles building, which is the math department, which is pure math, applied math, and computational math, all in one building. Then the tilings on the floor of the Andrew Wiles building are the Penrose tilings that we see here. Okay, well, let's move on a little bit further from the Arabic art into the Renaissance, where math made a humongous difference, and that is in the business of perspective. And perspective is the basically the use of mathematics in art to create the illusion of space and distance, but on a flat surface. And again, for a mathematician, if you do projective geometry or anything like this is kind of naturally what you do, but that mathematics sort of evolved out of the use of math in art to create this illusion, the illusion of trying to project a three-dimensional image onto a two-dimensional surface. And some of the heroes of all of this are the mainly Italian artist stroke mathematician. Again, where's the difference? Brunelleschi, Alberti, and Masaccio, Paolo Uccello, Francesca, and Pacchioli. And these were the pioneers of the notion of perspective, and they basically laid the foundation of modern art, and they laid it through mathematics. So here's mathematics creating essentially modern art. When I say modern art here, I mean, I don't mean modern art as in modern art, but I mean the art that we're used to seeing when we look at paintings nowadays. And the basic idea of perspective is to imagine the canvas that you're drawing on as a window into the outside world, and then you have vanishing points, and you line the walls and floors of your objects so that they line up with vanishing points, which are meant to be points at infinity. And you can have single point perspective if you have one vanishing point, or 2-point perspective if you have two. Okay, so this really was where kind of modern art started from mathematical point of view, and from mathematicians have taken this on way further into notions of projective geometry and projective space and stuff like that. And perhaps the most famous of all the Renaissance artists, who was also, of course, the most famous Renaissance scientist, and also, of course, one of the most famous Renaissance mathematicians. He was one of the first people to say that the laws of nature are written in the language of mathematics. Very good. Produced this wonderful picture, The Last Supper, which again, from a point of view of illusion, appears prominently in the Da Vinci Code, with all sorts of craziness associated with it. But you can see here how he is strongly using the notion of perspective in order to create the impression of depth in his pictures. But very much keep going on to the subject of illusion. One of the nice things about linking math with art is if you start playing games with the math, then you can create weird art which shouldn't really exist, but still looks rather fun. And here's a very nice picture that was produced by Hogarth in around about 1700, where he's taking the rules of perspective and deliberately applying them in the wrong way, so that you get this completely wrong picture, which creates an illusion of depth which is completely wrong in every way. I really like this, and you couldn't really do this picture. You've got to know the rules of perspective pretty well in order to be able to break them to produce this wonderful picture here. Okay, so that's how perspective worked. And now I want to take us up to the 20th century to tell you one of my favorites kind of stories about how math and art meet each other. And this is all focused around the wonderful work of Escher, who was born just at the end of the 19th century and lived until quite recently. And here's a picture that he drew of himself. And you can see that picture he drew shows his own complete understanding, not only of perspective, but also of the way that objects get reflected in well, in this case, in the sphere. There's a lot of great stuff. So Escher was an artist who lived in Holland and is incredibly famous for his basic fusion of ideas from geometry together with ideas in art into producing, as far as I'm concerned, some of the most characteristic and stunning art of the 20th century. He wasn't as respected by the artistic community as he should have been, I feel, precisely because he went outside typical artistic conventions and embraced mathematics to do his work. But I think we should wonderfully applaud him for this. And I first met his work. I don't know if you've ever read the book. It's when I was at university as an undergraduate back in the early 1980s. The book which everyone had to read at the time was by Douglas Hofstadter and was called Gödel, Escher, Bach. And it was just a wonderful fusion of the ideas in Bach, in Gödel and Escher all together. It's just an unbelievably amazing read and very much shaped the way I thought about mathematics both then and since. So here is a lovely picture that Escher drew of his own country in Holland. And you can see underneath you've got the kind of typical Dutch landscape. But then this is then brought out into this beautiful tessellation of the plane done using birds flying in these two directions. And it's called Darkness into Light. And I think this is just a stunningly wonderful picture. Another reason I like this picture is, as I say, it illustrates the Dutch countryside. My son is currently studying a PhD in the University of Delft in Holland. So before lockdown, we quite often go to Holland to see him, and hopefully we will soon enough be able to see him again. I'm sure are very aware of the International Congress for Mathematics, the ICM, which happens every 4 years and is the kind of the biggest conference there is for pure math, and is where the Fields Medals are awarded. And in 1954, the International Congress for Mathematics was held in Amsterdam, which is where Escher was living at the time. And one of the people that went along to the International Congress was Donald Coxeter, who is illustrated top right, who was professor of geometry at the University of Toronto up to around about 2003. He was still active right up until when he died in 2003. And Coxeter was regarded by many people as one of the greatest geometers, if not the greatest geometer of the 20th century. And the ICM, in a very sensible plan, decided to have an exhibition of Escher's work. And Coxeter met Escher at that exhibition and started a fantastic correspondence where you see the maths of Coxeter and the art of Escher again coming together in an amazing way. And one thing that really intrigued Escher was how you could visualize notions of infinity. And he was greatly impressed by a picture that occurred in one of Coxeter's papers. Coxeter was interested in hyperbolic geometry, so he was looking at how you take hyperbolic surfaces and put patterns onto them. And if you draw a triangle on a hyperbolic surface, it has the rather nice feature that its angles add up to less than pi. So Coxeter tessellated a hyperbolic surface and then projected that down onto the plane and came up with the picture that I've put down in front of you as a hyperbolic tessellation. And Escher was blown away by this. He loved the way that you've got this kind of tessellation which goes out to the perimeter of the circle, with the triangles getting smaller and smaller as you approach the outermost part of the circle. And this started a lovely correspondence. So sorry, there's lots of words here, but this is lifted directly from a letter from Escher to Coxeter in 1958, where he's referring to the paper that Coxeter wrote on crystal symmetry and its generalizations. And he says, it's simply much too learned for a simple, self-made, plain pattern man like me, which is ridiculous because he was anything but simple and was basically a genius. But he then basically says, I'm interested in patterns with motifs getting smaller and smaller till they reach the limit of infinite smallness. Then goes on to rave about how wonderful this picture is and how he basically took that picture and turned it into a woodcut. Unbelievably brilliant technical ability that Escher had to turn mathematical shapes into woodcuts. Escher wonderfully replied, Coxeter wonderfully replied, you know, I really liked the fact that you enjoyed my picture. And by the way, I'm sorry, this is all kind of like this and lots of words, but if anyone's interested, I can give you all the references. And then he started asking himself mathematical questions, whether there are other systems beside this one to reach a circle limit. And he says, yes, there's infinite number. And then he goes on to talk about how it happens. I wonder a little bit how Escher responded to this wonderful letter. But suffice to say, Escher and Coxeter remained firm friends and corresponded frequently right up to Escher's death in 1973, which was, you know, 15 years after this correspondence. So what did Escher do? Well, there's Coxeter's picture from his paper, which was, to say, constructed using the hyperbolic geometry. And that's what Escher did with it. He produced this astonishing picture, the tessellation, which called Angels and Devils. Unbelievable picture there. I hope you can see you've got devils in black, angels in white, and this tessellation extends right out to the boundary of the circle, closely following the hyperbolic geometry that Coxeter introduced. Okay, so that's Escher and Coxeter. It's worth saying that Escher worked with other mathematicians as well, and we already met Roger Penrose when we looked at the aperiodic tunneling of the plane. I'm proud to say that Roger Penrose, well, he's still alive, he was recently awarded the Nobel Prize, and rightly so, for his work on black holes and singularities in relativity theory. And I was at Oxford doing my PhD whilst he was at Oxford, and I had the privilege to attend some of his lectures. So I feel a small connection with this great man. And Penrose worked with his father to create mathematical objects which defied geometry. So again, this is a talk about a meeting about math and illusion. And on the left, you see a triangle with 3 right angles. Well, you kind of can't easily produce that. On the right, we have a staircase, which if you look at it, you can carry on going up without ever stopping. Penrose also corresponded with Escher. I think that they might have met at the ICM as well, but their correspondence took a little bit longer to get going than that with Coxeter. But anyway, it was very, very fruitful and led in part to this picture that Escher produced, where you can see people going up, infinitely up, or equivalently infinitely down a staircase in a building like this. So it's a wonderful area where an example of an optical illusion caused by a mathematical idea being harnessed by a great artist. I'll finish talking about Escher by telling you about what he actually regarded as his greatest piece of work, and is certainly from a mathematical point of view absolutely wonderful. And this is this piece of work, which is called the Prentententoonstelling, which my Dutch isn't very good. It should be better given my son's there, but means the printing room. The printing room. What's happening here, well, you can see a person looking at a picture in a gallery, but the pictures carry on extending and then evolve into the building that the gallery is held in, and then that building becomes part of a town with a sea, and then that town with the sea becomes part of the picture in the gallery that the person is looking at. So you have recursion here. You've got a recursion creating this wonderful illusion, going back again to the subject to this conference, where the person is looking at a picture and that picture is of the object of which that person is actually in. Unbelievable. And Escher created had a hole in the middle. We'll see why there's a hole there, and signed his name in that hole. And this illusion is an example of what's called a Droste pattern, named after the an advertising can, where here's some coffee with so I assume she's a nun, having some coffee, and there's a tin on by the coffee, and if you look on the tin, there's a picture of her holding a tin, and this picture kind of goes, it's the same picture. So the picture is within the picture, which is within the picture, which is within the picture, creating this wonderful illusion of infinite depth, one by one. And that's what we see here. And the way that Escher created this was that he started with a base design. So there is the picture of the person in the print gallery looking at the pictures. And then he wrapped it onto this grid here. So you may not recognize this immediately, but this is a set of elliptic curves, which is constructed over the complex plane. And I'm not quite sure where Escher got the idea of this from, but you can kind of very quickly appreciate the kind of mathematical structure that this is happening. And what he basically did was he took this image here and wrapped it around this geometry to produce this astonishing picture here, with this illusion of the picture within the picture within the picture within the picture. So there we are, and you can go off and see that in the Escher Museum in Amsterdam. But of course, there's this problem with it. It's got a hole in the middle, and that hole is that hole there, which Escher wasn't quite sure what to do with. And Lenstra, who is a professor of mathematics at the University of Leiden, felt that this was unsatisfactory. And whilst, of course, he couldn't match Escher's artistic genius, he felt that he might be able to use a bit of mathematics to fill in the hole in the middle. And what he and his team then did was take Escher's picture and continually reproduce the elliptic curves within the hole in the middle to produce the same kind of image, but now allowing you to have recursive depths. And now we have the gallery leading into the picture, which leads into the gallery, which leads into the picture, which leads into the gallery, which leads into the picture, and so on. And therefore was able to mathematically complete Escher's work without the hole in the middle. I shall leave it up to you to tell me whether you think that's aesthetically better or worse than Escher. But I think this is a nice point to conclude this talk on, because this shows how the fusion of mathematics and art, or art and mathematics, or art and mathematics all together, can produce an amazing piece of work, which at the same time gives us this amazing illusion of being both within a picture and outside it at the same time. And I think at that point, I will say thank you very much. There we go.
Thank you so much, Professor. We have some questions in the chat. Let's see. First of all, someone was wondering what tool Coxeter used to produce his original hyperbolic tessellation that Escher copied.
What tool did he use? I don't think he did very much more than think about it. I mean, he was an astonishing geometer. I very much recommend that you go off and have a look at his work. And so he would basically do it by thinking about it, thinking about what the curves would look like in the hyperbolic geometry, working out the equation for those curves, and then projecting it down, and then drawing the surface according to the equations that he then produced. And there's some very nice articles. My colleague Sarah Hart at Gresham College has written a very nice article about the actual mathematics of how Coxeter produced his hyperbolic tessellation.
Okay, thank you. Somebody else is wondering, can you suggest any reading materials which has more examples like this that we can study? And I believe that is referring to both the Escher paintings and the examples of distortions that you were just looking at.
Right. I've written some articles on this. I could, and they've got lots of references in them. If I was to bung them over to you, would that help? That might use some ideas. But I'm a great believer in going back to the original. Go and have a look at some of Coxeter's stuff, and using good old-fashioned Google, typing Coxeter and Escher, sorry, and you'll find lots and lots of examples of how this all worked. And as I said, there's a very nice article by my colleague Sarah Hart at Gresham College on Coxeter. So I keep using the word Exeter, it's where my wife comes from. Coxeter and Escher's work, which goes into much more mathematical detail.
Okay. Let's see. Another question we have is, are you familiar with the work of Heinrich Heesch? I'm not sure if I'm pronouncing that right.
I'm afraid I'm not. I'd like to know more if it sounds good.
Okay. Let's see. We have a question. Does Leinster's completion actually have no hole, or is the pattern repeated until the hole is too small to notice?
Okay, that's a very, very critical question. Leinster's construction, and by the way, if you go onto Leinster's website, there's even a movie which tells you how he does it. And if you go to the University of Leiden, on all of the walls of the maths department, you can see these pictures. It essentially goes on it goes infinitely deep into it. So the mathematical construction goes right into the singularity, and what Leinster did was just as much as he could to get the picture to look right. Okay, so in that diagram, I guess you can contract the, I guess, bad region down to a single point where things don't sort of line up. There will be a single point, but of course it's just a single point, rather than the kind of circle that Escher left. Okay, do we have any other questions? I'd like to ask one. Oh, wait, we do have another one. Are there instances of symbolic mathematics being culturally accepted as artistic? I guess that would mean sort of are there societies out there where mathematics is considered as art? Yeah. Oh, that's a good question. I'm not quite sure how to answer it. I mean, many different cultures, you'll find the same sort of mathematical ideas coming up as being regarded as equally beautiful. So, for example, in the indigenous cultures in North America, you see lots of examples of the same sort of thing. Symbolic maths just in its own right, I'm not so sure, but of course music is an example where you get symbolic maths turning into notes, turning into art, which people can enjoy. And I was thinking, I was hoping to have a bit of time today to talk a bit about dancing, but in the end I didn't. But folk dancing is another example where permutation groups, exactly the groups we're used to, dihedral groups and so on, can produce beautiful choreographic patterns in dance. But effectively, that's a whole extra talk. I believe, just based on my personal knowledge, there's a during the isolation period of Japan, during the feudal era, there were these geometric proofs that were prepared, and they did sort of have symbolic language. It was a combination of symbolic language and pictures. They're prepared these works that looked very much like art, although they were complete proofs of various geometry theorems. Oh, wonderful. I'd like to look up more of those, yeah.
I had a question.
Yeah, Richard.
I remember reading a few years ago that people were saying that the Penrose tiling pattern had actually been discovered in something like an Islamic art from 500 years ago. And I was wondering if you knew what that was about.
Not that I'd heard. I've always understood that Islamic art was basically periodic tilings rather than.
I see.
Tiling. So if that's the case, I stand corrected, and I would take that my comment. But
I mean, possibly it wasn't Islamic art, but it was, art from 500 years ago. But anyway, I'll try to dig this up.
I've just noticed that someone in the chat has put, "What about knitting like your jumper?" That's exactly why I've worn this jumper today. Thank you for making that observation. This is exactly the purpose of this jumper. I should say I like wearing jumpers when I teach my students so that they can kind of enjoy mathematics. And knitting, yes, is another beautiful example of where math meets art. And a lot of it is group theory, by the way.
Oh, and someone in the chat reminded me that the Japanese proofs I was telling you about are called Sangaku. You can just look them up. There's lots of written about them online.
Oh, wonderful. Well, the nice thing about talking about these sort of things is you learn so much from everyone else. And thank you very much for doing that.
Someone else pointed out cellular automata, and apparently during a Cambridge train station.
Well, cellular automata very much can produce art, and they basically operate by the fact that if you operate relatively simple rules, you can get great complexity coming out of them. And something else which I never touched on in this talk was fractals, which is again where simple rules can produce astonishingly beautiful pictures like Julia sets and Mandelbrot sets. It's just there's so much you can say, and say the conference that I referred to at the beginning is huge and very buzzy and lots of stuff going on, and also, I mean, another area of art which I haven't talked about was a couple of years ago. I was one of the organisers of the International Origami Conference, and there's a huge origami, and it's almost endless.
Someone just asked about origami tessellations, so that's a good connection.
Yeah, it's Lang, Robert Lang, who's a mathematician stroke origamiist, is doing fantastic things. I mean, it's almost limitless, and I say that where does math start, finish, and art stop? They're so fused together.
Chris, I wanted to say this is a shawl that my wife knitted. It's the Sierpinski carpet.
Ah, fantastic! What a great wife.
Yeah, she's a fiber artist. Anyway.
And there's people that do crochet art with mathematics. There's wonderful stuff out there. It's almost limitless, and I see your trousers look quite artistic as well. So can I congratulate your wife on her wonderful art, stroke maths.
Again, thank you so much, Professor Budd, for giving us that wonderful presentation.